All right, so now we're going to be looking at a impulse turbine question. It says here that steam discharges axially from a velocity compounded two-stage impulse turbine. So that already tells us that there will be two sets of moving blades, and in between those two sets of moving blades there will be a row of fixed blades that isn't turning. And all of those blades, so the two sets of rotating blades, will be connected to the same shaft. And they say that the steam discharges at a rate of 60 kilograms per second. That's our mass flow rate, M. Then they tell us that inlet and the exit angles of the first row of moving blades are equal. The inlet angle of the fixed blades is 35 degrees. And then they tell us that there's no axial thrust. So that's very important. No axial thrust is developed in the second stage. The outlet angle of the second row of moving blades is 30 degrees, and steam discharges from the turbine with a velocity of 80 meters per second. And the velocity coefficient for all the blades is 0.93. All right, then they ask us to draw the velocity diagram, and they give us the scale here. 4 meters per second equals 1 millimeter. Okay, so before we begin, like I said earlier, this sheet where it shows what an impulse turbine usually looks like, and a reaction turbine, and what it looks like when the steam is discharged axially from the turbine. That sheet we need to look at, and we need to know what all the different angles are and what the different velocities are. And like I said previously, what I suggest is that you really memorize what the different angles are, where they are on the graph, or on the diagram, I should say. And then when you read the question, so that's usually what it looks like, the velocity compounded velocity diagram. So that's the first set of moving blade, and that's the second set of moving blades. All right. Once you know more or less what it'll look like and where all the velocities and angles are, then you can start taking the information from the question and putting it on a rough diagram. All right. So what I like to do is, before I begin, I like to write down the information that they've given us. All right, so what they did give us is they gave us the mass flow rate of 60 kilograms per second. They told us that the coefficient of friction, or the velocity coefficient for all the blades, is 0.93. And they told us the scale was 4 meters per second equals 1 millimeter. And then they gave us information for the first row of moving blades and the second row of moving blades. So I separated those two. And it says here that, at first it says here, the inlet and the exit angles of the first row of moving blades are equal. All right, so if you look here on the sheet here that I gave you guys, here's the inlet angle and the outlet angle of the first row of the moving blades. So that is theta and phi. All right. So they're telling us in the question that those two angles are equal. And where are they on the velocity diagram? They're over here. So the first row of moving blades over here. And those two angles, theta and phi, are equal, because those two angles have to do with the angle of the blade. All right. So they have written it down. Theta equals phi. All right. Then what did they tell us? Then they told us that the inlet angle of the fixed blades is 35 degrees. All right. And then I wrote beta equals 35. Okay. So if we look at the diagram again, here we go. So beta. Okay, so it's saying that beta equals 35 degrees. Now, beta, what does it say here? It says that beta is the steam that leaves the blade. Okay, so there it says there, beta is the steam that leaves the blade. So as it moves over the blade, the angle that it leaves the blade is at beta. Okay, so what has that got to do with the fixed blades? So as you know, that as it leaves the first set of moving blades, it goes into the fixed blades. And what they want to do when they design this this turbine is that as it leaves the moving blade, that angle that it strikes the fixed blade at will be at that same angle as it leaves the moving blade. Okay, so you need to know that. So that angle then, 35 degrees, is beta. Okay. Then it says here that there is no axial thrust developed in the second stage. Now, what does that mean? So if we go to the second stage over here, it means that 2vf1, okay, so the velocity of flow must equal 2vf2, the velocity of flow. So the velocity of flow at the across the blades, so vf1 equals vf2. So there, I've written it there. At the second row of moving blades, 2vf1 equals 2vf2. Okay. Then it says the outlet angle of the second row of moving blades is 30 degrees. Okay, so where is that? So the outlet angle of the second row of moving blades, so we go down here, the second row of moving blades, and we see that the outlet angle for the blade is phi. Okay, so it's that one there, the outlet angle, and then we find it on the diagram, and we know that this is phi 1. Okay. Then it says steam discharges from the turbine with a velocity of 80 meters per second. So that is the velocity that the steam is leaving the turbine. And where is it leaving the turbine? So that'll be in the second row of moving blades, and it will be 2v2. So it will be, so it says here v2 is the velocity of the steam outlet. Okay, so 2 indicates that it's the second row of moving blades, and v2, it means that it's the velocity of the steam at the outlet. So it's this vector over here, and that is at 80 meters per second. And what else they say? Then they say the coefficient. Okay, we've said that before. And oh yes, at the beginning of the question, it says here that the steam discharges axially. That's very important. So it means that the steam coming out of the second row of moving blades, so this angle of beta here, it's not going to be as it's drawn here, but it's going to look like over here. Let me get to that. Over here, it's going to exit at 90 degrees. So this is what the second row of moving blades, the velocity diagram for the second row of moving blades will look like. All right. So we need to insert all that information now. So what I've done is I've drawn a rough sketch here of what it might look like. So there's the first set of moving blades, and there's the second set of moving blades. And all I need to do now is just write everything on. All right. So first of all, for the first set, theta equals phi. All right. So we're going to put over here. So let me get my sheet here. So theta must equal the same as phi. All right. And we said that beta was 35 degrees. That was the inlet angle of the fixed blades. Okay, so it means that the steam that's leaving the first set is leaving it at an angle of beta, and that is 35 degrees. So that's beta there. All right. And then very important, the next set, now we can go to the second row of moving blades. And if we see over here that it says 2VF1, which is this one here, over there, 2VF1, sorry, out of the camera there, 2VF1 must equal to 2VF2. So those two are equal. All right. And then they say to us that the outlet angle of the second row of moving blades is 30 degrees. Okay. So the outlet angle of the second row of moving blades, it's this one, is phi 1. And remember, this is theta 1. So that's the inlet angle of the second row. And this is the outlet angle. So we know that this now is 30 degrees. Okay. And then they tell us that the steam discharges from the turbine at 80 meters per second. So this is this one here, 2V2. And that is at 80 meters per second. Okay. And lastly, remember, they say the steam leaves the second row axially. So that means that it leaves at an angle of 90 degrees. All right, so now that we've got this information on the rough diagram, we need to know what the velocity of the moving blade is, okay? So remember, there's nothing wrong with going from information from the second set of moving blades to the first set of moving blades. So if we can know what the velocity is over here, we'll know what it is for the first set, because remember, these two sets of moving blades are moving on the same shaft. So they gave us the angle of the outlet of the second set of moving blades. They gave it to us as 30 degrees. And then they also told us that the steam discharges from the second set of moving blades axially. So that means that the angle which the steam leaves this turbine is at 90 degrees. So we have that. And then they also gave us the velocity of the steam that leaves. So that's V2. And they said that's 80 meters per second. And because of that, it's very easy for us to calculate what U is. And we can just simply use trigonometry for that. And you can see over here. So we can just say tan phi 1, so that's 30 degrees, equals opposite over adjacent. And they gave us what the opposite vector is of 80 meters per second. They gave us that. And so then we can very easily calculate what the adjacent is. So what we do is we're just going to say 80 divided by tan 30, and there we have it. So 138,564. So that's going to give us 138,564 meters per second. And then we just have to divide that by 4 meters per second, and we're going to get a length of 34,6 millimeters. All right, so now we know how long to draw this, 34,6 millimeters, and it's going to be the same for the first set of moving blades up there as well. All right, so next we have to start actually drawing this thing to scale. All right, so now we're going to plot this information to scale. And I've already started doing it, and I'm just going to explain to you what I did here. So to start with, we calculated what U is, the velocity of the moving blade. So we calculated what U is. And remember, it's connected to the same shaft, so this U is the same as that U. Okay, we calculated it to be 138,56 meters per second, and we divided by the scale, and the scale is 4 meters per second equals 1 millimeter. So we divide this number by 4 and we get 34,6 millimeters. So that's how long the line is we need to draw. So I've drawn it here. So 34,6 millimeters from that point to that point. And remember, for the first row, it's going to be the same. So I take my ruler and from that point there to that point there. And I know that that line now must be also 34,6 millimeters. So you can see they line up there. The beginning and the end line up. And that's important to make sure that they line up. All right, and then the outlet steam, V2. They told us it's 80 meters per second. So we have to divide it by 4 because of the scale, and we get 20 millimeters. So from that point to that point, it's 20 millimeters. All right, then we can just join up this point to this point now. Or we could have just used trigonometry. But if we join this point to this point and we measure it, so we measure it with the ruler like that, then I got it to be about 40 millimeters. So now we know what the relative velocity 2 is. So that means it's the outlet steam, VR2, relative to the moving blade. So that's that line there. All right. And now, how can we get what the relative velocity 1 is? Now, obviously, that speed there, if we go backwards now, so if we move backwards along the blade, that's where VR2 is at the bottom of the blade. If we get back to the top of the blade, obviously that's before the friction. So it means that the relative velocity after the blade has to be less than the relative velocity before the blade. Okay, so what we do is we calculate it. So this one here, VR1, all we do is we say VR2 divided by K, the coefficient of friction, and that's going to be 40 divided by 0.93, and we get the answer to be 43 millimeters. 43 millimeters, and that's what we expect. So VR2 is 40 millimeters, and VR1 is 43 millimeters. But now we don't have an angle here, okay? So what we do, if we take our compass, and here's my compass here, and my ruler, let me get it there, and I'm going to measure off 43 millimeters. Okay, so now my compass is set to 43 millimeters, and I put it on this point over here, and I make an arc. Okay, so there I made my arc there. You can see it very faintly. There's an arc. Okay, so all along that arc, from that point along the arc, it's all 43 millimeters. All right, but now I still don't know where along this arc I must draw it because I don't know this angle. See, I don't know that angle. So now what I do is they gave us a hint. In the question, they said that, and let me just get my page here. They said in the second row of moving blades, VF1, the velocity of flow, VF1 equals VF2. Okay, and we know what VF2 is because the flow is axial. So it means that V2 also equals VF2. So we know what that is. All right, and that's 20 millimeters. So we just have to draw a line at the bottom here. So we draw a line across there, and we know that all along that line, it's going to be 20 millimeters. Okay, and then we know VF2 equals VF1, and that is the point there that the two vectors, the relative velocity 1 and V1, converge. Okay, so then we can just join them up. We can join this line here from that point to that point, and we obviously know that's already 43 because we used the compass, and then we can join this line to this line, and then we know what V1 is, and that's 75.4 millimeters. All right, and now we have to go from the second row of moving blades to the first row of moving blades. Okay, and we know that the inlet steam to the second row of moving blades had to be faster when it left the first row of moving blades. And the reason why we know that, because as it left the first row of moving blades, it had to go through the fixed set of blades. Okay, so it moved through the fixed blades and it lost some of its velocity. And we know that the coefficient is the same for the fixed blades. So K is 0.93. So what we do is we calculate it. So we know this is 75.4. And then we say V2, it's going to be 2V1 over K. So that's going to be 75.4 divided by 0.93. Sorry, it's out of camera. And then we get 81.07 millimeters. So again, it's increased because we're going backwards now. So it's what we expect. So it means that when we go to the top here now, we know what the angle is because they told us what beta was. So it's 35 degrees. And now we know that this line needs to be, so we measure it to be 81 millimeters. So we know that point there. And then we can join this point to this point, and that will be the relative velocity 2. And I measured that to be 111 millimeters. Okay. Then this angle here, this angle is phi, and we can measure that angle to be, well, I measured it to be 24.7 degrees. All right. And so I take my protractor and I measure that to be 24.7. And then what I have to do then is I have to figure out what is theta. And they told us, they said for the first set of moving blades that theta equals phi. So they said those two angles are equal. So if I know this angle, I also know what theta is, which is also 24.7 degrees. So I measure that off and I make a line. So there I made just a line, but now I need to know how long is that line going to be. Okay. So again, and this line is relative velocity 1. Right. So obviously, if we have relative velocity 2, relative velocity 1 has to be greater again because it moved along the blade and it lost speed when it got to relative velocity 2. So this has to be, so again, we calculate it. VR1, it's going to be VR2 divided by K. So that's 111 divided by 0.93, and we get 119.35 millimeters. Again, this one is less than this one because of friction. So now we got 119.35 millimeters, and that's what we expect. And we measure that. Now we have to set we know that where the line is, but we have to actually measure that. So go to 119. Okay, so there it is there. So there's the line. So now we know where that is. And then to finish off, we can just join the two lines up. So like that. And that line now is the actual velocity 1. That's the inlet velocity of the steam. And we measure that to be approximately 153 millimeters. Okay. So that's how you draw the velocity diagram to scale. So after that, they might ask you some calculations. For example, the axial thrust and the power, and we'll do that in the next segment. All right. So in the question, they will usually ask you to give them all these angles and these velocities. So whenever you need to give them the velocity, so say if you want V1, you just have to say 153 millimeters, and you just times it by the scale, and you'll get the actual velocity. All right. So that's quite simple. Then they will also normally ask you these two calculations here. So they want the axial thrust. Okay. So for the turbine, the steam is obviously flowing through the turbine, and it's putting a force, an axial force onto the moving blades. And it's very important to know how much that axial thrust is. So here's the formula here. So axial thrust equals the mass flow rate, which is 60 they gave us, open bracket, Vf minus V1. So it's on the diagram here. So, okay, firstly, so this part, this one here, is for the first row of moving blades plus the force from the second row of moving blades. And if we look at the diagram, what's Vf1? So this, we have to measure this length here. So that's your velocity of flow 1 and minus the velocity of flow 2. Okay, so that's for the first set. So that's that there. So we get that to be, so I got this to be 50 millimeters minus 46,5 millimeters. And I had to multiply that by the scale, 4. Okay, so I minus those two, and then I multiply it by 4 for the scale. So you mustn't forget that. And then for the second set of moving blades, remember they said there was no axial thrust? And we'll see that because Vf1 is 20 millimeters and Vf2 is also 20 millimeters. So when you put it into the formula, 20 minus 20 equals 0. And you would also normally multiply it by the scale, but you don't have to because that's 0 now. And once you calculate that, you'll get 840 newtons. Okay, so again, it's just Vf1 minus Vf2 plus open bracket Vf1 on the second row minus Vf2 close bracket. Okay, so that's the formula. Very simple. And then for the power is also very easy to get. So for the power, we're looking at not the velocity of the flow, but the velocity of whirl. Now the velocity of whirl is what's actually causing the turbine to turn. Okay, so that's the component that's causing it to turn. So that's this one here, the velocity of whirl for the first and the velocity of whirl for the second. So again, you have to measure that. So I got that to 209.7 millimeters. And for the second row, I got that to be 72.7 millimeters. Okay. And you have to multiply that as well by the scale. So the formula is the mass flow rate times the velocity of the moving blade, which is u. So it's m times u times the velocity of whirl total. So it's this one for the first plus for the second. Okay, so I've got it here, 60 times 138.4. Remember, that's the actual velocity of the moving blades, u. So that's u. Open bracket now, 209.7 millimeters plus 72.7 millimeters. And remember, you must times that by the scale, and then you get, I got 9.38 megawatts of power. Okay, so yeah, just so you remember, if we look at this picture here, just so you know these two components. So the velocity of flow, so here's the moving blades here, it's rotating. Okay, and you have the gas coming in here, or the steam coming in at an angle. Remember, it's coming in at an angle through the nozzle, and that angle we know already, whatever that was over here, it's coming in at an angle, all right, and it's getting broken up into two components. Okay, so the component that's moving, in this case, it's down. You can also look at it sideways like this as well. Okay, so if you look at it coming in here like this component of this from this angle here, that component is pushing that way. Okay, and it's pushing, so that'll affect the bearings that this turbine is sitting on. And this component over here is what's actually causing this thing to spin. So that's pushing these buckets, or these little cups, to cause this turbine to, or the blades I should say, to cause this turbine to turn. Okay, so the velocity of whirl causes it to turn, and the velocity of flow is where it goes and pushes this thing downwards. So yeah, two very important things to know. So that one, the velocity of whirl, can tell you what the power is, and the velocity of flow tells you how much force is being pushed onto the bearings of the turbine. All right, so I hope that helps.